Alright, so in this video we're going to be looking at the chain rule. So the chain rule is what we use to find the derivative of a composite function. A composite function. So composite functions should be something that you've seen before, but just in case you forgot, the name or what we're referring to, a composite function is really just a function within a function, right? So if we have something like f of g of x, we have this function g of x within the function f of x. So it's like, multiple layers here, like an onion, right? So this is a composite function. So how would we find the derivative of something like that? Well, for that we use the chain rule. So the chain rule. So what is the chain rule? Well, if we have a function and we're trying to find its derivative, trying to find the derivative of that, let's say this composite function f of g of x, we're really working our way from the outside to the inside. So we find the derivative of the f of x component, leaving g of x alone, and then we multiply the inside. We multiply by the derivative of the inside. So what do I mean by that? So what I mean is we end up with f prime of g of x times the derivative of what's inside, the inside function. So times the derivative of g of x. So this is going to be our chain rule. So if you want to write this down, this is the chain rule, and that's what we're going to be using for composite functions to find their derivatives. But first, it's important that when you're given a function, you need to be able to identify what the f and what the g of x are, right? What is the outer and the inner functions in a composite function? So an example of a composite function would be something like sine of x squared. If we have something like this, sine of x squared, this is a composite function. So what are the two parts here? If we were trying to find our f of g of x, the f, the outer part here, our f of x for this function would be sine x. So you notice we don't write sine of x squared, it's sine of x, just the original function. The outer function is a sine function, so sine of x. The inner function here, the g of x, would just be x squared. So separating it like this, we can see that what we would do in this case is find the derivative of sine and keep inside whatever the value here was. So we would have the derivative of sine. Inside, we would plug x squared in. So the derivative of sine is cosine, but we'd keep the inside as our g of x. So g, and then we would multiply then by the derivative of our g of x, of our x squared, which is just 2x. So this would be our derivative of the sine of x squared function using the chain rule. So, the main point here was to just identify what the inner and outer function are. So, for example, again, we have a function like the square root of ln x. This, again, is an example of a composite function. Try to pause the video and identify what our f of x and our g of x are in this composite function. So the f of x here is the outer part, right? The f of x would just be square root of x. That is our function. The inner function is the ln part. So the g of x here is ln x. So what we would do is find the derivative of x squared, the square root of x, but instead of x, we would just keep it as we would replace the x with the g of x function. So square root of x, but instead of x, so it's 1 over, but instead of putting in x here, we plug in our g, so ln x, multiplied by the derivative of ln x. So that's how we kind of approach these things, right? So again, one last quick example, if we had something like cosine of sine of 5x, here, again, it's much clearer. The cosine is the outer function, sine is the inner function. So r f of x is cosine, g of x is sine of 5x. All right. So now that we've kind of got this out of the way, let's look at an example question more thoroughly worked out. I kind of did a little bit of an example here because chain rule isn't very complicated or hard in execution necessarily. Students often just forget certain components or get mixed up because if you have a large enough function, it can get kind of messy. So just make sure you're keeping track of everything. So if we're given our function f of x is equal to x squared minus 7 raised to the 5th power. If this is our function, this is an example of a composite function. Looking at this, you'd have to realize, hey, this is a composite function, and I'd have to use the chain rule. So what are our two functions here? The outer function is just the to the 5th part, right? It is some x to the 5th is the outer function here, and the inner function is the x squared minus 7. So how do we go about chain rule? We found the derivative of the outer function, and inside of the function, we keep our g of x as it is, then we multiply by the derivative of the inner. So what is the derivative? How do we find the derivative for this, right? If we have the exponent rule, we bring down, or the power rule, we bring it down. So then it's 5 times, we leave this as it is, x squared minus 7 raised to the n minus 1. So 5 minus 1 is 4. Now we multiply by the inside derivative. The derivative of x squared minus 7 is just 2x. So we can multiply the things on the outside, and this gives us an answer of 10x times x squared minus 7 to the 4th. That's an x, and that's a 2. This is going to be our answer according to chain rule. All right, let's look at another problem. So let's say we have a function g of x, or function g of x, that is the square root of 6x minus 4. So here, the outer function is the square root of x, and the inner function is 6x minus 4. So what's the square root of x? We should know by now, again, how to find the derivative of square root of x, but just for the sake of demonstration, we remember that the square root of x is the same thing as x raised to the 1/2, which means it's just, we bring the 1/2 down and subtract 1, right? So it's 1/2 times x to the 1/2 minus 1. So it's 1/2 times x to the negative 1/2. Again, doing all of that, basically the derivative of this is 1 over 2 root x. But we remember that instead of x, we plug in our g of x there. Or we plug in the, I'm not going to say g of x because we use that again here, but we plug in the inner layer of our composite function. So this would be 1 over 2 root 6x minus 4, right? Multiplied by the derivative of 6x minus 4. What is the derivative of 6x minus 4? Well, that's just 6. So we can simplify this. We get 6 over 2 times the square root of 6x minus 4. Cancel this out and just get a 3 in the numerator, giving us an answer of 3 divided by the square root of 6x minus 4. And this is going to be our answer according to chain rule for this composite function. All right, that was kind of weird. This is our answer. Close enough. Okay, so now let's look at another one. Again, there's nothing too challenging here. As long as you can identify what the outer function is and what the inner function is, as long as you can identify these layers of the composite function, you should be all right. As long as, again, you're not mixing up different things there. Just take your time, identify the right parts, take the derivatives, and you're set. We just simplify that expression and we're done. So if we're given some function h of x, and we say this h of x is sine squared of 4x. Sine squared of 4x. How do we do this? Well, this is a composite function, obviously, but it might be a bit clearer that this is a composite function if we rewrite this as, this is the same thing as just sine 4x whole thing squared. That might make it a bit easier to see here. But these two are equivalent. So if we have this, clearly this squared is the outer function and the sine of 4x is the inner function. So what is our h prime of x? The h prime of x is just going to be, we bring the 2 down, so that's 2 times sine of 4x raised to the 2 minus 1, which is just 1. So it's just 2 times sine of 4x, right? Times, now we take the derivative of sine of 4x, and the derivative of sine of 4x, the derivative of sine is cosine, so this is cosine of 4x. And most students actually stop here. But you'll notice that this is actually, this function here is not, this composite function is not have only 2 layers, but it has 3 layers. We have the squared function, the x squared, we have the sine of x, and then we have the 4x. This is actually 3 layers. So that means we would have to now multiply by the derivative of 4x. So you do not stop here. That is a very common mistake. Do not forget that you take the derivative of whatever is inside of our cosine function, or whatever is inside of our function here. You'll notice that if we were given sine x, the reason why it appears that we're not doing that is because if we take the derivative of x, the derivative of x is just 1. So we're multiplying whatever we have by 1, right? So if we have a regular we have a regular sine function and we take its derivative, we get cosine of x. And technically we are multiplying by the derivative of this because this is a composite. So we multiply by the derivative of x, which is just 1. And so your answer remains the same, which is why you don't see it happening there. But if you're given an interior value here inside our sine function or a cosine function or any of your trig functions, this is another thing you have to take the derivative of. So the derivative of 4x is just 4. So I kind of went off on a rant there a little bit. The main idea here is don't forget to take the derivative of the inside. This is actually has 3 layers. Yes, that's the second layer. Yeah. So now simplifying this, we can see we have 2 constants in the front. We can multiply those out, giving us 8 sine of 4x times cosine of 4x. And this is going to be our answer for this problem. Now I wanted to show one more example here just to show you that there are multiple ways to solve the same problem. For example, if we're given a function where our function here, our f of x, is ln of x to the 5th, and we want to find this derivative here. Oops, okay, give me a second. Is it glitching again? Right, as I was saying, if we have a function f of x that is equal to ln of x to the 5th, for example, there are 2 ways that we can do this. We can identify the fact that this ln of x to the 5th is a composite function, where that outer function is ln of x, the inner function is x to the 5th, and do what we've been doing. So let's do that first and get an answer, and then I can look at a different way you may have tried to approach this, where you don't actually have to use the chain rule. But anyway, using the chain rule, we'll see that we get first the derivative, so our f prime of x, the derivative of the outer function, derivative of ln of x would just be 1 over x, but we put, again, x to the 5th. And now we multiply by the derivative of x to the 5th, which is 5x to the 4th. 5x to the 4th. We are then able to cancel out the x to the 4th, and then this x to the 5th becomes an x, right? So, if you want me to write that all out, we would see that we get x to the 4th here, which is equal to 5x to the 4th divided by x to the 5th. This cancels out, giving us 5 over x as our answer using the chain rule. So now, what is another way you can try to approach this where you don't have to use the chain rule? If you think back to our rules with logarithms, you can remember that we can actually rewrite this function. If we have a function where we have a logarithm with raised to a power inside there, we can actually bring that power to the front. So we can actually rewrite this function to be 5 times ln of x. 5 times ln of x. And now you can see that suddenly this has become a product rule question. So now we can use product rule to find this. So using product rule, the derivative, again, we would start with, well, you guys know how to use product rule, obviously. So this is just 5 times 1 over x plus, what's the derivative of 5? That's just 0. 0 times ln of x is just 0. So we end up with 5 over x as our answer. So we get the same answer here. So remember, you're not limited to one approach. If you're able to manipulate this function to be written in a way where you can use a different tool, then obviously all the that's your decision. Whichever you're more comfortable with doing, you should do that, and whatever takes less time. But anyway, that was kind of the point of this, was just to demonstrate that you can solve the same type of problem or solve the same function using different rules by rewriting it in a different form. But in any case, that's that's all I wanted to just to go over in this video. Any other chain rule questions that you may see is just going to be some variation of this, maybe some more elaborate question where, for example, if you had a fraction inside, then you'd have to use quotient rule, which obviously just makes things a lot longer and the simplification process. But at the end of the day, it's just algebraic manipulation and just simplifying different expressions. So as long as you keep track of all your terms and make sure you take your time there, there's nothing more really to talk about chain rule. So again, if this video is helpful, please show your support by liking and subscribing. Leave any questions you may have in the comments or anything you'd like to see in the future, again, in the comments, and I will see you in the next video.